Welcome to lecture 3. Today we are going to discuss about basic switch mode power converter topology. We want to cover primarily non-isolated switch mode power converters and a few isolated converters also. In this class only we want to limit our topological aspect because this course is primarily for control, modeling, tuning approaches. So, we just want to reinvestigate or just want to revisit the basic topology, switch mode power converter topology. So, here we will consider basic DC-DC converter, then step down, step up converter as well as step up down like buck boost converter and a few isolated DC-DC converters. So, step down converter, switching converter, which we discuss in lecture number 2 at the end, and we talked about inductive DC-DC converter. So, in this converter, it is a well known topology in which inductor and capacitor, like this inductor and capacitor is used to this inductor and capacitor is used for filter purpose, and we use a switch. This switch, it is a single pole single throw switch, and this switch is a complementary to S, and this S switch is operated by this gate signal Q, and this S switch is like a single pole single throw switch and will turn on and off by providing the gate pulse Q. When the gate pulse is 1, the switch will be on. When the gate pulse is 0, the switch will be off, and the S bar will operate in complementary fashion. So, if we turn on the switch Q, then the circuit is looks like this. That means you have like a parallel RLC circuit that we have discussed, in which input voltage like a DC input voltage, and you have inductor, capacitor and load resistance. When the switch is off, that means S bar complementary switch is on, then the overall circuit look like this. So, this is the inductor and this is the output capacitor and the load resistance. So, now if we look at the overall operation during when the switch is on, we call it as a mode 1, when the switch is off, we call it as a mode 2, and here we are talking about a synchronous buck converter, which have two which has two MOSFETs, like a high side and low side MOSFETs, and the MOSFET can carry current in either direction. So, in this case this buck converter will always operate in continuous conduction mode. So, that is why we are getting two configuration, mode 1 and mode 2. But none of this configuration, like if we continue operating in mode 1 like a on state, or that means during the on state the output voltage will at steady state will become input voltage. Similarly, if you continue to operate in mode 2, the output voltage will equal to 0, like it will get completely, the capacitor will completely get discharged. So, that means neither of these two configuration can be used to achieve the output voltage which we want to achieve, which should be higher than, which should be a positive voltage greater than 0, and it should be smaller than input voltage, because we want to achieve a step down DC-DC converter. So, we need to operate the switches in such a way so that we get the desired output voltage which is smaller than input voltage. Now, the question is, how can we switch? Particularly, how should we generate the on and off pulse of the main switch, which is a controllable switch, that is S, such that our desired output voltage is achieved. That means output voltage can achieve, we can achieve the desired output voltage in finite time. Okay. So, that means, as I said, the Q can be set to logic 1, then the switch S will be on, and when it is set to logic 0, the high side switch will be off and the complementary switch will be on. Here we are assigning time on time as T on and the off time as T off, it is slightly different from our conventional notation of d into t1 minus d into t, and the total time period is t small subscript small t. Why we are writing separately t1 and t off and the total time period? Because we are going to discuss in subsequent class that it is not necessary that total time period has to be constant, because there are different modulation technique in which, in one case we can keep time period constant. When under that condition, like if you keep the time period constant, then we can, if you vary on time, then off time will be automatically adjusted from the total time. The other possibility that we can change on time by keeping off time constant. We can change off time by keeping on time constant. In those two cases, the total time period can vary. Perhaps the third possibility that we can vary both on and off time. In that case also the total time period can vary. So, these are the possibility by which we can switch the main switch like a S in order to achieve the output voltage to its desired value. Okay, T on time of the switch S, off time of the switch S, and then the total time in a periodic cycle. But at steady state they must operate in a periodic fashion. That means at steady state the time period will be constant. But if there is a change in operating condition, the steady state condition can change, then depending upon how we are generating the timing constraint, the time period can also change. But when it reaches steady state, then that particular time the time period will be constant, total time. Okay. Now, this is well known like a volt second balance in a buck converter, any DC-DC converter. What is the volt second balance, that we know, but just to revisit the concept, if we consider the voltage across inductor, that means we are talking about this particular voltage, the voltage across inductor, this voltage changes its polarity when the switch status changes. For example, the VL for this buck converter is equal to input minus output voltage. So, the input voltage is the voltage across this terminal and the output voltage is voltage across this terminal. So, we are talking about this terminal and this terminal, these two are the terminal. So, that means the voltage across inductor is equal to input voltage minus V0. You can see the right hand side terminal is fixed, where the left hand side terminal the voltage can changes. If S is on, that can become input voltage. If S is off, when the S bar is on, then it will become 0 voltage. And this is shown here. So, VL can be V in minus V0 or minus V0 depending upon whether Q is on or 1 or Q is 0. Now, in this scenario, we are talking about this average inductor voltage. That means, if we take the average of the inductor voltage over a periodic cycle T, in this case T, the subscript, and we want to and this is well known that the average inductor voltage over a periodic cycle should be equal to 0. Why? Because the inductor voltage is nothing but it is proportional to the voltage across inductor, which is the induced voltage, is proportional to the rate of change of flux in the inductor. So, if we can ensure over a periodic cycle the average inductor voltage is 0, that means the average flux change over a periodic cycle will be 0. If we cannot ensure the average flux to be constant or the rate of change of average flux to be 0, that means the average flux should remain constant, then what will happen? If any residual flux that keeps on building in every cycle, then it can saturate the core. So, it can saturate the core if we either keep up building up or it can go down. So, anyway, depending upon the BH curve of the magnetic curve, it can saturate in either direction. So, we want that average inductor voltage should be 0. Now, before we move forward, we just want to make sure that the steady state notations are clear. So, all capital quantities represent the steady state values like a VL, V in, V0, then IL, I0, all are the steady state quantity. If we take the timing constant like a on time, capital T on, capital T off, then TSW is the switching period at steady state, and then FSW, which is the switching frequency, is equal to 1 by time period. Now, we want to go next. We want to check that from volt second balance, what is the inductor voltage? We know, we have already discussed that if you take the average, in the average sense, when the switch is on, the voltage across inductor is V in minus V0. And when the switch is off, then the voltage across inductor is minus V0. That means the voltage across inductor changes from V in minus V0 to minus V0, and what is our interest, that during on time this is a positive voltage. So, we want to show that this area under the curve during the on time period must be same as this area under this curve. That means their sum should be 0, so that the rate of change of flux should be 0 over a periodic cycle. And if we do that, the area under the curve, that means that VL, which is the average voltage, V in minus V0, then T on plus minus V0 T off, and whole thing divided by TSW should be 0, and this gives us the output voltage expression of an ideal buck converter in continuous conduction mode. So, this expression of output voltage in terms of input voltage and the timing parameters are somewhat different from what we are familiar with, that we always think of V0 is equal to D into V in, and that is the case when the time period is constant, then the T on by total time will be the duty ratio. But as I said, we want to take a variety of modulation technique where we need to know the individual timing parameters. So, that is why we kept in terms of T on T off terms. Similarly, if we take the capacitor current, if we look at this capacitor current always, it is always equal to inductor current minus load current. So, if you take the average over the periodic cycle, it will become the average of inductor current minus the average of load current. And again, under steady state, the average capacitor current must be 0, because the capacitor current is nothing but dq dt, that means rate of change of charge in the capacitor. So, at steady state, the rate of change of charge in the capacitor over a periodic cycle must be 0. Otherwise, if there is any positive charge that keeps on building, then the capacitor voltage will keep on increasing, and that is not permissible. So, that must be 0, and which leads to the average inductor current in this case is equal to average load current. Alright. So, now what happened for the boost converter? Again, these are the well known fact, but we just want to revisit once. So, here also you can draw the waveform of this boost converter, where this Q is my gate signal, that is the controllable switch for this S. Now, in this case, this is our controllable switch, and this is a low side switch, and S bar, which is a complementary switch, high side. So, this high side switch can be replaced by a diode in case of a conventional boost converter, and this is called synchronous boost converter, where we consider two MOSFET rather than diode, and they operate in a complementary fashion. So, S is the controllable switch which we are going to control using the gate signal Q, and S bar operate in complement with S. So, now we can see the inductor voltage. Inductor voltage, when the Q is high or S is on, then inductor voltage, if we take this terminal and this terminal, this exactly equal to the input voltage. When the switch is off, then the inductor voltage is equal to input voltage minus output voltage. So, V in minus V 0. Now, we can write down that inductor voltage equations, which is at different switch state when Q equal to 1 and Q equal to 0, and accordingly we can write the capacitor current. But interestingly here, if you look at the capacitor current, when the switch S is on, then this S bar switch is off. That means the capacitor current is equal to minus load current, because there the direction of the currents are reversed. I mean, IC is coming towards capacitor current, the notation, that is the positive direction of the capacitor current, and I0 which is going to the load, that is the load current which is going out of the capacitor current. So, their sum should be 0. So, as a result IC equal to minus I0. When the switch S is off, then S bar is on. In that case, we will see the inductor current here. That means this path will be inductor current when Q equal to 0. Okay. So, when Q equal to 0, we will get capacitor current will be IL minus I0, that is shown here. Alright. So, now we got the inductor voltage under two switch configurations, and again we can write down the notation. Then under steady state, what happened under steady state? At steady state, our input voltage, that means inductor voltage is equal to input voltage when the switch is on, that we discuss, and we are assuming that output voltage and input voltage are almost constant, that means the ripples are assumed to be negligible. So, you can write in terms of the DC quantity, and then we can again write the steady state on time and off time, and again we want to show that the area under this curve should be equal to the area under this curve, and if we can make sure these two areas are same, the area under the curve, then the average voltage across the inductor will be 0, and as a result the average change in flux over a periodic cycle will be 0. So, that means the flux will remain constant over a cycle under steady state, and this gives us the output voltage and input voltage relationship. So, output voltage is equal to, these are my timing parameters, and input voltage. Alright. Next, we can now draw the capacitor current, and we know that when the switch is on, this capacitor current will be minus I0. When the switch is off, it will be IL minus I0. Now, we can again write down what is the average capacitor current over a cycle, and that can be written simply from this graph, say waveform, and if we set it to 0 because we want the average capacitor current to be 0, then we can get the average inductor current is equal to average load current multiplied by this timing constant. Okay. Now, so we can find out the current gain, we can find out voltage gain from this relationship. But remember, we are still dealing with ideal DC-DC converter, whether it is a buck or boost, all are ideal. So, the relation is not so simple. In fact, it is not the correct relationship when we consider the parasitic drop, like for a practical converter, and that we will also discuss in subsequent lecture, but it is at least it is the basic point. I mean, these are the basic equation to start with. Now, if we want to write the voltage gain of any converter, we can write output voltage by input voltage. For step down, it will be smaller than unity, for step up it is greater than unity, and we want this kV to be positive because we want output voltage to be positive. For a boost converter, this voltage gain can be written like this, and for buck converter it can be written like this, and from here it is clear that this kV is greater than 0 and less than 1. for boost converter, we can see that the kV, the voltage gain is greater than 0, sorry, for boost converter, yeah, this kV can be shown to be greater than 1. That means it is higher than unity, so output voltage will be higher than the input voltage. Now, our ultimate objective is to regulate the voltage, whether it is a step down or step up converter, we want to regulate the voltage. In order to regulate the voltage, what can vary? As we have discussed in the previous slide, that voltage gain kV is V0 by Vin. So, we want to keep output voltage constant. That means output voltage we want to maintain, regulate, when there can be a change in input voltage, Vin. There can be change in load current also, although this voltage gain expression does not include explicitly the load expression, load current, but if we consider parasitic, that load dependent term will also come. So, our ultimate objective is to regulate the output voltage. Then how can we regulate the output voltage? When there can be variation in input voltage or there can be variation in load current. So, we can adjust T on by keeping TSW constant. We know the relationship that voltage gain is for a, if we take a buck converter, it was T on by T on plus T off. This is for buck converter, and this is for buck converter. Here, that means if we write V0, it is simply kV by V in. And what we want, if there is any change in V in, we need to accordingly adjust this voltage gain such that the output voltage is regulated. So, the first criteria, we can set this T on plus T off, which is nothing but switching period, that we can keep constant. And this, if we keep this constant, this is the condition I am showing, then we can regulate the output voltage by adjusting the on time. So, then since the time period is constant, the on time by total time is the duty ratio. So, essentially we are controlling the duty ratio, that is my control variable. So, I have to control the duty ratio in order to regulate the output voltage whenever there is any change in input voltage or load current. So, this technique is known as pulse width modulation. In fact, there are different variant of pulse width modulation like a trailing edge PWM, leading edge PWM, dual edge PWM, but in all cases the time period is constant, and depending upon whether we want to control on time or off time, that architecture differ. That different architectures exist for varying like a control variable, like whether we want to control the on time, off time, or sometime we can vary both on and off, subject to the constant, the total time period is constant. Now, the another degree of freedom which can be, we can adjust on time. That means it is same as earlier. Earlier also we adjusted on time by keeping total time period constant. Here we are adjusting on time but keeping off time constant. That means this off time is equal to set to the constant value, and the control variable is T on. When you write small t on, that means this is the instantaneous value, and under steady state we can write capital T on. That means the time period is equal to sum of this on time and off time, and if there is a variation in the voltage gain, then of course there will be a variation in time period, because we are keeping off time constant where on time can vary, their summation can vary. So, under this condition, if we write the time period expression, it will be a function of voltage gain. So, this is my voltage gain function and off time. So, this is something which is constant, this is constant. So, that means if there is any variation in voltage gain, because we want to regulate the output voltage, suppose there is a change in input voltage, then kV we are changing. If kV changes, this function changes, but the time of time is constant, so the time period varies. That means any variation in kV will also change the time period. The same thing is for boost converter, only the expression is different. Okay? So, this technique is known as constant of time control. The third possibility, that we can keep the on time constant. Now, earlier we did on off time constant, we kept the off time constant and vary on time. Now, we are adjusting off time, but this we kept is constant, T on. That means T on is kept constant. Control variable is the off time, which is the instantaneous off time, and again in this case the time period will vary, and we can get the expression time period, which is TSW, that is switching period, is a function of voltage gain multiplied by this on time, and this quantity is constant. That means we can find out that this TSW will vary when there is a variation in gain. Okay? That means there is a variation in off time. This technique is known as constant on time modulation, and we will also discuss some case study like subsequent lecture in detail. So, all these three techniques have certain advantage and disadvantage, and they also are very popular in their respective like a application, like a respective operating conditions also, or also kind of control technique that we use. Now, the third converter which is left is the buck boost converter, which is well known, where again this switch is the controllable switch and the other switch is actually used for as a complementary switch. And if we again draw the Q, that means the gate signal, and if we write down the voltage across inductor, then depending upon the Q equal to 1 and Q equal to 0, that means whether S is on or S is off, we can write down the inductor voltage and the steady state equation. Then if we carry out the volt second balance that we did earlier, we can find the output voltage is actually the negative of input voltage with a gain which depends on the on and off time. That means in this case we are getting output voltage negative, but if you take the magnitude of the output voltage, this magnitude of the output voltage can be higher than magnitude of the input voltage, it can be lower than the input voltage, but in this case it is negative. Output voltage is negative, the magnitude can be either higher or lower or even equal. So, this topology, there are other topology related to buck boost operation which can generate positive output voltage, and one of the topology is non-inverting buck boost converter, which is a potential candidate for low power application. That means this candidate is used for low power, and if you take the circuit diagram of this low power non-inverting buck boost, you can see there are 4 switches, but in general if you see this converter can be operated even in. So, this converter shows that if you break this converter into 2 parts, this side looks similar to the buck converter and this side looks similar to the boost converter. So, as if it is we are merging a buck and boost converter together, and there are 4 switches. This is the control switch S, and this is S, S bar and S bar. So, although I have used the same gate signal for S, but we can operate them independently. That means S and this switch and this switch can be operated independently also. So, that depending upon the requirement. So, if we set Q equal to 1, Q equal to 0, then we can get the required buck boost operation. If we want to operate this converter, like if we use independently, then it is possible to operate purely in the buck mode, it is possible to operate purely in the boost mode, and the current configuration where I kept here, if we keep this this, if we remove this bar, that means if you operate these two switches identically, this switch and this switch, and other switches are complementary to their respective switch, then this will operate like a buck boost converter with positive output voltage. Now, we just want to introduce isolated switch mode power converter, because in subsequent lecture we also want to take a few case study, so that whatever we will be doing, that is also equally applicable for isolated DC-DC converter. So, if we take the isolated DC-DC converter, this point is A, B, and this is the like a isolated, that means we are using transformer as a for galvanic isolation, but transformer cannot be used directly in the with a DC source. That means, if we use a DC source in either side of the transformer core can get saturated, it will get saturated. So, that means we need to convert this DC to AC, we need to have a conversion like a signal DC voltage to AC and AC to DC. But it is not necessary this AC to DC conversion, DC to AC conversion, the AC must, it is not necessary the AC has to be a sine wave. It can be a square wave, it can be a quasi square wave, but what we need, that the average value of this AC signal which is going through this, passing through this transformer, that must be 0. If there is any non-zero average value, then it will actually lead to transformer core saturation. So, we have to make sure that average value must be 0 at steady state. Now, the possible DC to AC configuration. So, it is simply like it is like our full bridge configuration. We are using 4 switches and we can set the gate signal of the 4 switches accordingly, like Q11, Q22, like this switch and this switch, we set it using a controllable gate signal Q, whereas the remaining switch S12 and S21, they are operated in a complementary fashion, like S12, this gate signal is operated complementary to Q, that means this is equal to Q bar, this is also equal to Q bar. In this case, what will happen, depending upon whether the switch is on and off, you will get VAB dash, that means the voltage across this terminal. If Q equal to 1, it will see input voltage, if Q equal to 0, it will see minus VAB, that means this input voltage is VAB, and if Q equal to 0, it will see minus of VAB. It is not necessary that these two switches has to be operated using a same gate signal, but it is necessary that S11 and S12, they must be complementary. So, we can operate them to generate quasi square wave also. In this case, we are talking about square wave, but even if we generate a square wave, this square wave will pass through this transformer, but the secondary side we have connected a resistive load. That means resistive load will see a pulsating voltage which a positive and negative polarity, that is VAB dash. So, we need to use a diode. So, if you use a diode bridge rectifier, then we can convert this AC signal to DC, but since it is not a pure sine wave, that means it is a square wave, so it will lead to harmonic. So, this resistance will not even, it may not see the pure DC voltage, because it may consist of some harmonics, higher order harmonics. So, in order to minimize the harmonic effect, we need to consider LC filter. So, this is my filter and this whole circuit is like a full bridge circuit, the full bridge circuit, where the first is, this is my inverter which is my DC to AC conversion stage, this is my transformer stage, this is my AC to DC stage, and this is my filter stage. The whole thing is a full bridge converter. Now, if we want to generate if we want to get the isolated version of the buck boost converter, we know that this side terminal is basically a pulsating voltage appears. Although this voltage is fixed, it is a negative voltage, but across this terminal VL, the right side voltage, reflection of this right side will appear like a pulsating voltage, okay, because it is the voltage across the inductor. So that means we can replace this voltage Vx now, where we start with a buck boost converter and this is a floating voltage. We will replace suitably. What will be this floating voltage? We will take into that. But across VAB, this floating voltage will appear like a pulsating voltage depending upon the status of switch S bar. So this can be replaced by a floating voltage, and if we take the floating voltage, now we have represented, what we can do, we can change the polarity of this floating voltage. How? By changing the dot convention of the transformer. That means if we change the dot convention of this transformer, this polarity of the floating voltage can be reversed, provided the input side voltage polarity remains same. We have changed the dot convention of the transformer. Now, if the switch is on, because this part is we are taking from after the inductor side of the buck boost converter, the regular buck boost converter, and we have used a transformer with this dotted convention. Depending upon whether the switch is on, then you will see the input voltage across this terminal where the inductor is connected to the left side. When the switch is off S, then S bar is on, then what voltage will be seen across VAB? VAB dash, it will see Vx minus Vx like here. Even though you are using a positive voltage, because of the dot convention it will appear as a minus Vx, and if we take the reflection of that voltage across VAB, we will get minus NVx, and then actually this VAB, it should not be minus, it will be plus, and if we take, because we are talking about this particular circuit, and if we take VAB, then it will have a negative because of the dot convention, and that means we can write the inductor voltage. Now the overall circuit, we can merge these two circuits. This part now we have merged it. Earlier there was inductor and this is the part of the buck boost converter. If you merge these two parts, then what we can do, the high side switch, we can take this switch to the low side. Complementary switch, this can be replaced by a diode, and Vx can be replaced by a capacitor resistance in parallel. That means a resistance and a because the resistance will act like a filter, capacitor will act like a filter, and the resistance is the load resistance. So now, and this inductor can be realized as an integral part of the transformer, which is a magnetizing reactance. So this actually represents the flyback converter. So by this variation and starting from a non-inverting buck boost converter, if we add the transformer and modify the circuit, then we came to the flyback converter. So flyback converter is an isolated version of non-inverting buck boost converter with a positive output. So in summary, we have discussed buck converter, step down purpose, step up purpose. We have discussed buck boost converter, both step up and step down purpose, but it was with negative polarity. We discussed about non-inverting buck boost converter, and we have also discussed some basic isolated DC-DC converter architecture. So with this, we will move to the other lecture that modulation technique and the steady state analysis. For today, and this is sufficient. Thank you very much.